Section. Introduction. We're here to talk about language agents, which are essentially AI systems that use language models to solve complex reasoning problems. These agents can perform actions, interact with external tools, and are crucial for tackling interactive tasks like answering questions, browsing the web, or solving mathematical problems. These tasks are challenging because they often require long-term planning and interactive reasoning. In the past, many of these agents have relied on large language model APIs like OpenAI's GPT-4 and ChatGPT. While these are powerful tools, they can be quite expensive, especially for tasks that require long contexts, like web tasks where you need to encode HTML. Plus, these model APIs are not always deterministic, which makes reproducing the agent's actions difficult. And because these large language models are closed source, we don't have a clear understanding of their internal workings. We believe that relying on these closed-source models isn't the best approach for the research community. Instead, we suggest using open-source large language models. However, recent studies have shown that agents built with open-source models don't perform as well as those using GPT-4. That's why we're introducing LUMOS, a new framework for building language agents. Unlike traditional fine-tuning methods, LUMOS focuses on creating a modular framework. It consists of 3 modules: a planning module that breaks down complex tasks into high-level subgoals, a grounding module that translates these subgoals into low-level actions, and an execution module that carries out these actions using tools like calculators and search engines. We've also developed 2 ways to implement language agents using LUMOS: LUMOS One-Time, LUMOS O, and LUMOS Iterative, LUMOS I. LUMOS O is an efficient method that generates all subgoals and actions in one go, while LUMOS I generates one subgoal at a time, making it more adaptive. LUMOS uses a unified data format that can handle a variety of interactive tasks, like answering questions, coding, web browsing, and more. This format is beneficial because it allows for cross-task generalization. To train LUMOS, we've converted the decision-making steps of existing benchmarks into this unified format with the help of GPT-4. This not only helps us gather high-quality training data but also facilitates cross-task generalization. We've collected about 40,000 training annotations for the planning and grounding modules, making it one of the largest open-source resources for fine-tuning agents. These annotations can be used to enhance any open-source large language models with agent capabilities. Our evaluations show that LUMOS performs exceptionally well across various complex interactive tasks, including intricate question answering, web tasks, and mathematics tasks. It outperforms GPT-based agents and even some contemporary agents that have been fine-tuned with in-domain annotations. LUMOS also generalizes well to unseen tasks and actions, suggesting that it could be beneficial for a wide range of language agent applications. In summary, we've developed a modular agent learning framework that trains open-source large language models with unified data, and it outperforms other learning methods. Our unified task representation and collected data can be instrumental for future research in developing open-source agents for complex interactive tasks. LUMOS surpasses GPT-based agents in intricate tasks and generalizes well to unseen tasks and actions. Section Summary. We propose LUMOS, an open-source language agent framework built on open-source language models, LLMs, which addresses the limitations of closed-source LLM-based agents. LUMOS consists of 3 modules: a planning module, a grounding module, and an execution module, enabling it to perform complex interactive tasks such as question answering, web browsing, and mathematical reasoning. Our evaluation shows that LUMOS achieves state-of-the-art performance across various tasks, outperforming GPT-based agents and demonstrating cross-task generalization capabilities. Section. LUMOS, a modular agent framework. We're excited to introduce LUMOS, a modular framework designed to help build intelligent agents. This framework is designed to tackle complex tasks by breaking them down into smaller, manageable subgoals. These subgoals are then transformed into a series of executable actions. This process is managed by 3 key components of our framework: the planning module, the grounding module, and the execution module. The execution module is essentially a program that translates actions into a series of operations. It uses a variety of readily available tools, such as APIs, neural models, and virtual simulators, to interact with the environment and carry out tasks. For example, if the task is to find information, the execution module could use the Wikipedia API or Google Search APIs to query a document. If the task involves answering a question, it could use retrieval augmented QA models or even GPTs. For mathematical problems, it could use the Wolfram Alpha APIs, and for web tasks, it could simulate clicking and typing operations using HTML simulators. The unique feature of the LUMOS framework is the interaction between the planning, grounding, and execution modules. We've developed two versions of this framework to enhance communication between these modules: LUMOS One-Time, LUMOS O, and LUMOS Iterative, LUMOS I. LUMOS One-Time, LUMOS O, is a highly efficient method that generates all subgoals and their corresponding actions at once. In this version, the planning module generates all subgoals in a single step, without needing to interact with the other modules. These subgoals are then passed to the grounding module, which translates them into a series of actions. For example, if the task is to find out how long a person named Lowell Sherman lived, the grounding module could generate actions like query Lowell Sherman on Wikipedia, and retrieve paragraph with the query, how long did Lowell Sherman live? The grounding module is guided by action interfaces, which define the functionalities of actions and their valid arguments. In the LUMOS O version, the planning module takes the task description as input and generates a series of subgoals. The grounding module then takes these subgoals, along with the task description and action interfaces, and generates a series of actions. On the other hand, LUMOS Iterative, LUMOS I, generates one subgoal and its corresponding actions in each iteration. This version is more dynamic as it takes into account the results of previous actions when planning the next subgoal. This allows the system to adapt to changes in the environment. For example, if the task is to find out which state the US president in 2014 was born in, the planning module would first generate a subgoal to find out who the president was in 2014. After finding out that it was Obama, the next subgoal would be to find out which state Obama was born in. In the LUMOS I version, the planning module takes the task description, previous subgoals, and their results as input to plan the next subgoal. The grounding module then takes this subgoal, along with the task description, action interfaces, and previous actions, to generate the next set of actions. These actions are then executed, and the results are used to plan the next subgoal. This process continues until the task is completed. Section Summary. The LUMOS framework introduces a modular agent architecture for solving complex interactive tasks by decomposing them into subgoals and converting them into sequences of executable actions. The framework consists of planning, grounding, and execution modules, and offers two formulations. LUMOS One-Time, LUMOS O, generates all subgoals and grounded actions simultaneously, while LUMOS Iterative, LUMOS I, generates one subgoal and its corresponding actions in each iteration, adapting to dynamic environmental changes. Section. Learning to plan and ground with open-source LLMs. We're working on a project to improve the planning and grounding modules of open-source language learning models, LLMs. Our goal is to enable these modules to generate subgoals and valid low-level actions. To do this, we need high-quality task descriptions, subgoals, and low-level actions for training. In the past, smaller LLMs have been trained to follow instructions using methods like self-instruct, which creates instructions, inputs, and outputs based on seed examples. However, these methods aren't suitable for complex interactive tasks. For instance, GPT-4 only achieves a 20% success rate in a web agent benchmark called Mind2Web. If we were to use these methods for complex tasks, it could introduce noise and lower the quality of the annotations. Instead of creating annotations directly with API-based LLMs, we use LLMs as a tool to convert existing intermediate reasoning steps into the format we need for our project, which we call LUMOS. We've found several complex interactive tasks that have been annotated with either human-written solutions or structured action sequences. These tasks provide a wealth of fundamental information that we can use for annotation conversion. To help LLMs follow the conversion instructions, we add 4 or 5 in-context examples in the conversion prompts. These examples have important properties that we'll discuss later. All the converted annotations are denoted with a hat over the letters. The intermediate executed results, denoted as E-hat, are crucial for increasing LUMOS's adaptability to environmental changes. Some datasets, like GSM-8K and Mind2Web, provide execution results in their reasoning steps. We use these as E-hat. For datasets without execution results, we use the relevant documents that contain clues for solving subgoals. For example, in the strategy QA dataset, the question, "What color skin are zombies typically depicted with?" doesn't have a direct answer. However, the annotation includes a related fact that mentions the answer, green. So, for each in-context example, we combine the relevant documents and our manually captured execution results in the conversion prompts. This way, when we convert new samples into our expected annotations, LLMs can automatically extract answers from the given documents as the executed results. After prompting LLMs with the conversion prompts, we can obtain the key elements in training annotations, including subgoals, S-hat, their corresponding actions, A-hat, and execution results, E-hat. We also use a conversational grounding module annotation. In this process, we first play the role of a user to provide the task, T-hat, action space, and interfaces, I-hat. For the LUMOS O formulation, we include all the subgoal annotations, S-hat, in the first user prompt. All the action annotations, A-hat, would be the response to the user instruction. For the LUMOS I formulation, we include the first subgoal annotation, S-hat, in the first user prompt. The response of the grounding module should be the corresponding actions, A-hat. As the style of LUMOS training annotations is conversational, we format them as a series of user prompts and their responses. During training, we feed each multi-turn annotation into a decoder-only model and calculate the decoding loss on the tokens of ground truth responses. We apply binary masking on the user prompt tokens to prevent computing loss on them. The final loss function is the negative sum of the logarithm of the probability of each input token, multiplied by a Boolean indicator function, only for the tokens in the ground truth responses. Section Summary. To train planning and grounding modules for generating subgoals and valid low-level actions, we fine-tune them using high-quality task descriptions, subgoals, and low-level actions. Instead of relying on methods like self-instruct, which may introduce noise and degrade annotation quality, we use LLMs as a style transfer tool to convert ground truth intermediate reasoning steps from existing benchmarks into the expected format in LUMOS formulations. We also leverage execution results and relevant documents to increase LUMOS's adaptability to environmental changes and transfer annotations into conversations for training. Section. Experiments. In this section, we'll walk you through our experimental setup and the results we obtained from testing our system, LUMOS. We'll explain how we evaluated LUMOS's performance by comparing it with other open-source language learning model, LLM, agents and GPT-based agent frameworks, contrasting our approach with other potential open-source agent baselines, assessing LUMOS's ability to adapt to new tasks and environments, and evaluating the quality of our training annotations. To tackle complex interactive tasks, we incorporated commonly used actions into predefined action spaces. Think of each action as a function that takes in intermediate results and outputs text. For example, the action knowledge query, entity, can produce detailed information about any given entity, using methods like Wikipedia Search Index or Google Search APIs. We tested our agents on a variety of complex interactive tasks, such as complex question answering, web, and math tasks. We followed the evaluation standards set by Agent Bench and Rewu. The performance on each task type is shown in a table. It's important to note that task-specific agents like LUMOS I_X are trained using data specific to task type 10, e.g., web, math, QA. We compared LUMOS with other existing agents powered by open-source LLMs. Our findings showed that LUMOS consistently outperformed various open-source LLM agents across all 5 datasets. Even though the base models of the compared language agents are about 2 to 4 times larger than LUMOS in terms of model size, LUMOS significantly excelled in performance. For instance, LUMOS achieved 24.5% and 14.1% step success rate improvements over WIZARDLM30B and AGENTLM70B, respectively, on the Mind2 web dataset. LUMOS I also scored 1.6% higher than code LLAMA34B. Interestingly, even without any fine-tuning using Hotpot QA annotations, LUMOS I still showed impressive improvement. We also evaluated the effectiveness of the modular design in LUMOS. For a given task T, the agent learns to generate all the subgoals and actions using the same model. The execution modules remain the same. This training approach, which does not use modular design, is adopted in Rewu Open, FireAct, and Agent LM. From our results, both LUMOS I and LUMOS O significantly outperformed vanilla training and COT training. This further emphasizes the advantage of distinguishing between the skills for sub-goal planning and action grounding during the training of language agents. Another benefit of modular training, as used in LUMOS, is the ease of generalizing to new tasks and actions, which can be achieved by incrementally updating the grounding module while keeping the planning module unchanged. LUMOS's design allows it to adapt well to new tasks. When faced with a task that was not present in the training data, LUMOS can adapt to it more effectively with few-shot examples. To test this, we used WebShop as the unseen task. WebShop is not a typical web task as it doesn't involve HTML pages or simulate operations like clicking and typing. Instead, it uses a web shopping scenario to create an interactive environment. To adapt LUMOS to this new task, we supplemented the input of the planning and grounding modules with two-shot examples. As a result, LUMOSI achieved a 5 to 10% higher average reward than domain-specific agents on WebShop. It also significantly outperformed larger language agents such as WIZARDLM30B and Vicuña 13B. This suggests that unified training enables agents to improve their ability to plan for unseen tasks and action types. Section Summary. The experimental setup of LUMOS is described, including the integration of commonly used actions into predefined action spaces and the evaluation of its performance on complex interactive tasks. LUMOS consistently outperforms larger open-source language models, demonstrating its effectiveness. The modular design of LUMOS is evaluated, showing that it outperforms other training paradigms and allows for easier generalization to new tasks and actions. LUMOS also exhibits superior cross-task generalization ability, as demonstrated by its performance on an unseen task, WebShop. Section. Further analysis on training annotations. Further insights on training annotations. In our examination of annotations, we're looking to answer two key questions related to the quality and structure of our work. The first question is, how effective are the training annotations we've converted? The second question is, would it be more beneficial to use low-level subgoals instead of the high-level subgoals we've proposed? Comparing low-level subgoals and high-level subgoals. As we've previously explained, we encourage language learning models, LLMs, to generate high-level subgoals that can equate to one or more low-level actions. Another possible approach could be to have each subgoal correspond to just one low-level action, which we could refer to as a low-level subgoal. We guide LLMs to produce these annotations with low-level subgoals by adjusting the in-context samples to match the format where a subgoal is directly tied to a single action. We then analyze complex question-answering tasks, as each subgoal in the revised question-answering annotations is connected to more than two low-level actions. As shown in our table, we find that performance drops when we replace high-level subgoals with low-level ones across both question-answering datasets. This outcome thus confirms the suitability of our original subgoal design. Enhancing small models to develop general agents. Knowledge distillation is a widely used method for transferring knowledge from larger models to smaller ones, thereby improving efficiency. Many recent studies have used LLMs to generate explicit textual knowledge or training data to train smaller models. We've noticed that generating annotations directly for training planning and grounding modules can lead to a significant number of errors, especially since robust LLMs, like GPT-4, show low performance levels on some complex interactive tasks. In our approach, we don't use LLMs to generate training annotations without any reference. Instead, we use LLMs to convert the gold reasoning steps into our preferred annotation format for training system modules.